Hello everyone, this is a video on the equivalence principle in its weak form. In this video, I want to show that gravitational and inertial mass have the same numerical value as a consequence of the fact that perturbations in the gravitational field move at the speed of light. To make my point, I will start from the fact that Newtonian gravity is an instant action at distance where fields have not kinetic energy. Modify Newtonian gravity to take into account that perturbation in fields move at the speed of light, as we already know from relativity. Show that this gives kinetic energy to fields. Show that when a mass is moving, its gravitational potential will move with it. At a given point in space, close to the moving mass, fields will change in both amplitude and direction. Show that the integral of the kinetic energy of field's variation in the whole space is exactly equal to 1/2 the mass times the velocity squared. This means that the kinetic energy of a moving mass is actually the kinetic energy of the fields generated by the mass and vary in space. At the end of the video, I will perform a full calculation to show that this is true. This will finally lead to the equivalence principle because the very same fields that are generated by a mass are the ones that give inertia to the mass itself. This is not a standard approach you find in books, but bear with me up to the end and decide by yourself if what I say can possibly make sense. In Newtonian gravity, if we move a mass in the solar system, the effect on the gravitational potential of this action is seen immediately in the whole universe. This is because the equation of the Newtonian gravity is the Poisson's equation, where phi is the potential and ρm is the density of distribution of matter in space. This equation has no dynamics for the fields because it hasn't any time derivative in it. For this theory, it is possible to define a density of potential energy associated to field, but does not make any sense to define a density of energy associated to the field rate of change in time. And this is fine because this theory is just the classical limit of the theory of general relativity applicable to masses that move very slowly compared with the speed of light. We want to modify Newtonian gravity to take into account that perturbations in fields move at the speed of light. We need to introduce time derivatives. Since the Laplacian is made of second derivatives with respect to spatial coordinates, the obvious thing to do is to add a second derivative with respect to time. We get the wave equation. With this equation, perturbations in fields move at the speed of light, and when the velocity of masses goes to zero, also the time derivative goes to zero, and we get back the Poisson's equation. Now we want to find a mechanical system which is described by the same equation of the modified Newtonian gravity. This is an easy task since many systems are described by the wave equation. We choose the propagation of longitudinal waves in an elastic medium. We are not saying that space is an elastic medium. We are saying that since the two systems are described by the same equation, if we find a property in one system, this property must belong also to the other system. The equation of waves in an elastic medium has two parameters. Rho is the density of the medium, and y is the Young modulus of the material. The negative gradient of the potential, which is a vector representing strains with negative sign, is the equivalent of the gravitational fields, with a proportional factor to take also into account units, since gravitational fields has unit of acceleration, while strains are dimensionless. This equation is valid for infinitesimal displacements, otherwise the system cannot be described by a linear equation. In the mechanical system, we can easily define a potential energy density proportional to the modulus square of the strains and a kinetic energy density proportional to the modulus squares of the time derivative of the displacement. Since in the mechanical system there is kinetic energy, we conclude that also in the modified Newtonian gravity, fields changing with time have kinetic energy. So far so good. We have an elastic model to describe the gravitational field in empty space. In this model, strains in the material represent the gravitational field. Now we need to introduce in the model a point mass, or at least a mass very concentrated around a point. To do that, we start from empty space, and we remove a ball of material of radius r. We pull the boundary of the hole in the material from a radius r to a much smaller radius eta. We find out that strains in the material have a spherical configuration and go like 1 over r squared with distance. If we take strains with opposite signs, this is exactly what we need to model the gravitational field generated by a point mass. The equation to evaluate displacement and strains in the material is once again the Poisson's equation, which in turn is the wave equation for static fields, where the time derivative is zero. We want to find an expression for the displacements induced in the elastic material by a singularity of missing space. We start from the Poisson equation in spherical coordinates for a solution that has a spherical symmetry and that depends only on R, and we see that this is a Cauchy-Euler differential equation. The general solution depends on three constants. We know that the potential is equal to the amplitude of the displacements, and therefore by solving for the potential, we are actually solving for the displacements. From the boundary condition at infinity, where displacement are 0, we see immediately that the constant k1 and k2 are 0. And from the boundary condition at eta, on the radial coordinates, we find easily k. With the assumption that r is much greater than eta, we find eventually the displacement. We call m the quantity r times eta. This is our mass at eta's unit of square meter, since it is the product of two lengths. By taking the derivative of the displacement with opposite sign, we have mu, which is the field of strains, and which is the equivalent of gravitational fields in our model. Before we go on, we need a final assumption. The mass is the product of r and eta, but we'll assume that for all masses, eta is always the same, a kind of constant of nature, and the mass will be determined by r only. This seems a strange and unjustified assumption, but this is essential for the whole concept to work out. We are ready now for our final calculation. We want to evaluate the integral in the whole space of the kinetic energy of the fields changing when a singularity is moving along the x-axis. When the singularity moves, displacement will change in space according to the position of the singularity. Elementary volumes, represented by red diamonds in the video, will go along a loop at a velocity depending on how far they are from the trajectory of the singularity. But elementary volumes have mass and therefore have kinetic energy. To proceed with the calculation, we notice that displacement for points on the xy plane have no z component. Moreover, the solution has a cylindrical symmetry. This means that we can evaluate displacement on the xy plane and get displacement in space just by rotating the result around the x-axis. Since the mass is moving at a low speed compared to the speed of light, we can approximate displacement with the displacement induced by a mass at rest and moving rigidly along with the mass. Displacement in space and time are a composite function of u tilde, which represent displacement for a mass at rest in the origin, and the function x minus sigma, where sigma is the position of the mass on the x-axis and varying with time. The derivative with respect to time of the displacements is therefore minus the derivative with respect to the x-coordinate of u tilde times sigma dot. Since sigma dot is the velocity of the mass, the modulo square of u dot is the modulo square of the derivative of u tilde with respect to the x-coordinate times the velocity square. The rest is just algebra. We start from the expression for the displacement of a mass at rest in the origin with respect of r and theta, shown in the picture. We substitute the value r and theta and we get an expression in terms of the x and y variable only. With a bit of effort, we manage to simplify this expression. This expression is valid in the first quadrant only because of the sign of the arcotangent. It is possible to show that the final expression for the modulo square is symmetric with respect to the xz plane, and therefore the final expression will be valid in the second quadrant where x is negative. Once we have the displacements, we can evaluate the derivatives of the component of the displacement with respect to the x-coordinate, and we can evaluate the modulo square of these derivatives. After a few simplifications, we get a very simple expression in the x and y coordinates. At this point, we need to go back to the spherical coordinates, which are more convenient given the integration set gamma. And the final step is to integrate this expression in gamma, which is the whole space minus the ball of radius r centered in the origin of the axis. Now we can finally put things together. We start from the expression for the kinetic energy. We know that the modulo square of u dot is the modulo square of the derivative of the displacement with respect to x times v square. We substitute the expression for the integral of the modulo square of the derivative of u tilde with respect to the x-coordinate, and we find an expression for the kinetic energy. We know that by definition m is r times eta, and we see that the kinetic energy of the gravitational field is proportional to the mass and the velocity square of the discontinuity of missing space. If we go back from the elastic model to the Newtonian gravity by converting the mass from units of square meter to kilogram, then we can always choose the constants in the brackets to get the well-known expression for kinetic energy. This proves the point we made at the beginning of the video, because the kinetic energy of a mass is due to the very same gravitational field that make masses to attract each other, and therefore gravitational and inertial masses must have the same numerical value. There are two final points. In Newtonian gravity, the self-energy, which is the potential energy stored in gravitational field of a mass, and that is required to create the mass, is infinite because the modulo square of gravitational field is not integrable. In the elastic model, following the same approach used for the kinetic energy, we can evaluate the potential energy of the fields, and since we remove from the integration domain the ball of radius r, we get a self-energy which is finite. Choosing the constant in the model for getting the correct kinetic energy and the correct force masses are attract each other, it is possible to show that this self-energy is equal to mc squared. Finally, it is possible to evaluate the conversion factor for a mass from square meter to kilogram between the two models. We call this conversion factor Km. This conversion factor turned out to be very small since, for the mass of the known particle, we get a radius r much smaller than the Planck length, and this is bad. However, for a mass of order of magnitude of a Planck mass, we get a radius r of the order of magnitude of the Planck length. Thanks for watching.